Good morning, everybody. I'm Rebecca Santamaria-Fernandez, Director of Industry Partnerships and Commercialization Engineering at Imperial Enterprise, and I'm delighted to welcome you all today to our fourth Imperial.Tech.Pitch event, focusing on innovation in engineering using artificial intelligence and machine learning. With this event, which we're co-hosting with our colleagues at Imperial Business Partners, we're hoping to bring some of the amazing work that goes on at Imperial to your workplaces or your home offices. At Imperial, our mission is not just to understand the world, but to have an impact on it and to change it for the better. And we're doing this through world-leading research and education, turning great academic thinking into impactful innovations. At Enterprise, we support our Imperial staff and students on the enterprising journey, and we connect them to businesses like yours. Our team is passionate about developing and commercializing Imperial's academic discoveries, and impact is really at the heart of what we do. Today, I really hope that we can give you a snapshot of Imperial's data science, AI and machine learning research capabilities and some of the amazing technologies and how we're applying this to solve engineering challenges such as wireless video transmission or control and process optimization that might enable decision making in complex environments, with applications in a variety of sectors such as technology, energy and biopharma. These are challenges we cannot face alone, and we need you and your organisation to help us change the world. We're delighted to have my colleague Professor Michael Huth as our chairperson today. Michael is head of our computing department, and he will tell you a bit more about Imperial's efforts to tackle these challenges in a minute. Then we have lined up 4 awesome speakers that will showcase our research capabilities and technologies, which are available for licensing in this space. We're also fortunate enough to have 2 industry speakers from engineering firms such as Hitachi and Imperial startups PSE acquired by Siemens, joining our discussion today.
Hello, I am Michael Huth, head of the Department of Computing. I want to thank Rebecca for the nice introduction, and I share her excitement about today's pitch event on AI, machine learning, and data science for engineering. There can be no doubt that computing and digitization are co-shaping the world of tomorrow. 30 years ago, a Finnish student, Linus Torvalds, began a personal project, a new free operating system kernel, Linux. In 2013, Google's Linux-based Android had 75% of the market share. Linux is freely available, yet many companies, including those in the financial sector, profit heavily from it. In AI, machine learning, and data science, we see similar trends. ML frameworks such as TensorFlow and Keras, AI models for natural language processing such as T5, and programming languages such as Julia for data science are freely available and support a powerful environment that nurtures for profit research and development in startups, SMEs, and large companies. Our 4 pitch talks exemplify application domains in which such value creation is extremely promising. The digitally driven innovation in pharmacy, in renewable energies and sustainability, in communication technology, and in personal transportation systems. We are proud of the work that Maria, Matthew, Dennis, and Oytun and their teams are doing. They excel in applying the tools of the digital age to science and engineering problems to create products and services for a better world.
Hello everybody and welcome to this presentation. I'm going to give you an overview of the activities of my lab in the space of mathematical modeling, and to be more specific on how we use data-driven modeling and machine learning to assist the development of novel therapeutics. So before we kick off with research, a little bit about us. That's my team over here. We're a new lab, so we started April last year when I started my appointment with Imperial College. And so today we count 3 PhD students, that you see on the slide. as well as 5 master's students and 6 undergraduate students as well that they do research in the lab. The lab's main focus is essentially to take Industry 4.0 principles and apply them in life sciences, and to be more specific, in biopharmaceuticals. So we are focused on developing digital tools, so that is nothing else than computer modeling tools, essentially, to assist the decision making primarily in the manufacturing of therapeutics, but also in the distribution as well, as I'm going to show you in a little while. And we have 3 main, if you like, targets. The first is that we always have to be responsive to the needs of the patient, so to be responding in a timely manner, but also to achieve production of high quality products, to essentially meet all the target quality attributes as they are laid out by the regulators, and finally to use those computer modeling tools to gain control over our processes and ideally move towards more automated solutions. One of the main areas where we work on, essentially, and I'm going to focus on this presentation, is monoclonal antibody production, where at the moment most of the processes are operated in batch or semi-batch mode, and there is a growing demand for those therapeutics. At the same time, from a modeling perspective, the models are quite complex, and so what we're trying to achieve in the lab is to couple the needs of the market and the challenges of the research, if you like. We put the two together and we create mathematical tools that are not simplistic, but actually they are easy to use and user-friendly, to primarily understand our processes better and then eventually be able to improve them and control them. And I'm going to briefly focus on a case study where we looked at the development of a hybrid tool. So that's the combination of mechanistic modeling with neural networks to describe a cell culture model. So in this publication that you can see at the bottom of the slide as well, we looked at cell culture systems of CHO cells for the production of monoclonal antibody. And what we wanted to achieve is to design a tool essentially that we will be able to use online. So what you see on these graphs, at the bottom graph, at the top right graph, you can see the agreement between the experimental data, the hybrid model, which is the combination of the data-driven model that describes the glycosylation procedure, and the mechanistic model that describes the mass balances and the like, and how those essentially have a good performance. And at the bottom of the slide, you see the application of this hybrid tool, if you like, in a more online manner, where we assume that we have disturbances in our feeding strategy. So what we did in this work is that we used the data-driven model to bring the system back to the optimal performance. And so overall, we would say that we developed a tool of reduced computational complexity and better suitability for online applications. And this work also expands into downstream processes too. And finally, just to close off, similar work is now looking at disease understanding and therapy discovery, manufacturing, and timely distribution. So our lab is looking at the development of such tools all the way from therapy discovery to therapy distribution. Thank you very much for watching, and I'll be happy to take any questions.
Hi, my name is Matt Picker. I am Professor of Computational Geoscience and Engineering in the Department of Earth Science and Engineering at Imperial College London. Today I'm going to be telling you about our work on physics and data-driven tools to support the development of offshore renewable energy systems. First, some motivation. This photo shows interactions between wind turbines in the atmosphere. Turbines extract momentum from the wind, leading to a wake characterized by a slower, more turbulent flow. Further changes to the flow also occur that accelerate and decelerate the wind within and around the entire farm. Together, these are termed wake and blockage effects. This means that there are better and worse locations for turbines to be placed in relation to one another, as well as better and worse ways in which each turbine is operated, as both impact on the wakes turbines generate. If we don't account for these in yield prediction tools, we'll potentially overpredict the farm's performance. The move to greater numbers of larger turbines means that this is a growing issue. This movie demonstrates that it is indeed possible to simulate wakes to high accuracy numerically. Here we see the wake from the upstream turbine has a significant impact on the downstream turbine. The power plot here is showing the power of the downstream turbine, and we can see the drop in power as well as the variability, which will have an impact on fatigue loading. It is therefore important to have accurate models which, given inputs such as the layout or the operation of the farm, output reliable estimates of farm yield. However, it's almost never the case that we only want to perform a single calculation. Generally, we want to iterate on one of these input parameters for design, control, or uncertainty quantification purposes. But now we have a problem. We are forced to limit the cost of each model run, but also we need the model to be an accurate representation of the real world. There's little point in optimizing the design within a numerical world which bears little resemblance to the real world, for example. In our work, we're exploring a number of research directions to address this challenge, including use of both process or physics-driven models combined with data-driven or machine learning approaches to provide accurate but highly efficient models of real-world processes. Current design tools typically simplify device-to-device interactions and ignore blockage effects. We're developing tools where the farm design and its operation is fully coupled to the flow. Here in this example, we see how the power varies as a 2D response surface based on lateral and streamwise spacing parameters for this idealized array. Each pair of parameters considered requires a numerical simulation. So for example, if we considered 5 spaces in each direction, we'd have to run 25 simulations to map out this surface to find the optimal spacings. In contrast, in this movie, we see how the optimization algorithms we are employing are able to efficiently explore a much larger design space using a relatively small number of iterations and hence model runs. By allowing more design flexibility, we arrive at a layout that yields 18% more power than this example. Early on, it's driven by avoiding negative wake interactions, but later on, it manages to exploit blockage effects in this idealized channel. This gives us a good platform for the optimization or control of turbine farms, but we still need to address the issue of physical realism. This is where machine learning has a role to play. Here we see the application of a purely data-driven model of a wind farm to the control problem of wake steering. The yaw angles of turbines are controlled in order to steer their wakes away from downstream turbines. In this particular case, a convolutional neural network is used to provide rapid estimates of the flow within the farm and hence its total yield. This in turn is fed into optimization algorithms. Now, this is an example of a purely data-driven approach. Our current research is focused on the combination of process-based and data-driven methods. This includes through student projects under our MSc programs in Applied Computational Science and Engineering and Environmental Data Science and Machine Learning, for which we are very enthusiastic for industry collaborations. Here are some examples of some of the recent projects in the areas of AI, modeling, and energy. So in summary, we're developing a range of tools to act as digital twins of renewable energy systems. We're particularly interested in the physical and computational challenges associated with the coupling between turbine layout and operation and the underlying fluid dynamics that provide the renewable resource. We see the combination of process and data-driven approaches, or so-called physics-informed machine learning, as being vital in addressing the realism versus cost issue. Collaboration with industry and access to data is of course vital. I will leave you with a more complex farm optimization example. Here, the optimization of 256 turbines are optimized in a complex tidal flow. Thank you for your time.
Hello, this is Deniz Gündüz. I'm a professor of information processing at Imperial College London. I will present an artificial intelligence-aided wireless video delivery technology that we have developed in my research group. Even before the pandemic, video content accounted for about 66% of mobile data traffic. And of course, after the pandemic, we spend most of our days attending video calls, watching video lectures, or streaming movies. And we are all too familiar with the so-called spinning wheel of death, the loading icon that we experience in case of a weak wireless connection. So the main ambition of our technology is basically to remove the spinning wheel from our lives. Now, to give better context, let me first briefly explain how video is delivered to our mobile devices today. So the video signals are first compressed into bits using a video compression standard such as MPEG or H.264. These compressed bits are then delivered over a wireless communication channel. And for reliable delivery, we employ digital modulation techniques or error correction codes to mitigate the adverse effects of noise over the channel. Now, this digital approach suffers from the so-called cliff effect. So which means that if the channel quality becomes worse than what the channel code is designed for, we cannot recover the bits. So we basically the transmission fails and we basically observe the spinning wheel. On the other hand, if the channel quality gets better than expected, we do not get better quality reconstruction as we already removed the part of the information during the compression stage. Now, what I propose is a completely new approach. Basically, we will employ a pair of deep neural networks to act as the encoder and the decoder, which we train jointly. Now, so there are no bits, no digital modulation, and no explicit compression or error correction code in our technology. So we get rid of all these existing components and directly map the video input to the parameters of the waveform that is transmitted over the air. Now, let's see an example. Here, basically, I present the reconstructed video as the channel quality measured by the signal-to-noise ratio, SNR, decreases. So for the state-of-the-art digital transmission scheme on the right-hand side, as the channel quality gets worse, at some point the code cannot sustain the transmission anymore. That is, we hit the cliff edge and we see the spinning wheel. Now, to recover the image, we need to switch to a different code that delivers a lower quality video with more error protection. On the other hand, on the left-hand side, the video transmitted by our technology, DeepWive, not only achieves a better quality reconstruction at all points, but we also never see the spinning wheel. So at even very low channel qualities, we still manage to recover a reasonable quality video at the receiver. Now, there are many other advantages of our technology. For example, we can easily incorporate video intelligence functionalities, such as we can count the number of people in a surveillance video instead of reconstructing it, which wouldn't be possible with the conventional approach. DeepWive is also 10 times faster than the conventional schemes, and it can easily adapt to specific domains. For example, we can easily train it for just for drone images, and the improvement with respect to the digital approaches will be even more significant. Also, basically, our technology can bring the benefits of faster transmission, better quality, and robustness against channel variations to a wide range of applications, from drone video transmission to streaming applications and even to professional video production industry. Okay, thank you very much for your attention.
Hello everyone, my name is Oytun Babacan and I'm a research fellow at the Grantham Institute with an expertise in sustainable energy systems. Together with my partner Daphne Tuncer, who is an expert in communication and computer systems, we established EvoTrack. EvoTrack is a software technology company. It develops advanced data analytics for public charging infrastructure to ensure its optimal planning and operation. We created EvoTrack because we want to ensure infrastructure deployment to be as smart and sustainable as possible. Countries are going through major transformations in their infrastructure towards decarbonization, and electric vehicles are often in the spotlight of their climate strategies. As a result, we expect several million charging stations to be deployed in the UK, in European Union, and around the world. In day-to-day operation, charging providers want their stations to be used at their best capacity. However, they also need to provide a good level of service to all their customers. The charging network should be reliable, provide affordable service, and convenient access. Evo-Track develops state-of-the-art tools that makes network operation and expansion more cost-effective and sustainable. Our tools will reduce the capital burden on charging providers, making their services more affordable to their customers. Thanks to our technology, providers will be able to invest their resources in regions that need charging services the most. Our mission is to limit the carbon and energy footprints of our charging infrastructure. With that, I will now pass the word to my partner, Daphne Tuncer.
Thanks, Oytun, for introducing our mission. In Evo-Track, we believe in data-driven tools to address the challenges of future charging station deployment. We apply state-of-the-art data science techniques to control the life cycles of charging stations, from monitoring how they are used at different times of the day, to understanding patterns in how they are accessed, and forecasting future needs in specific areas. Our solution builds upon novel data management frameworks for collecting, cleaning, and processing charging-related data. It also uses learning-based algorithms that are specifically tailored to the electric vehicle domain space in order to identify main factors influencing the demand. All our tools are designed using best practice data standards. We, as such, ensure that quality procedures are integrated at every stage of the data processing pipeline. Our electric vehicle data science solution helps decision makers in determining where it's best to invest in order to deploy charging stations. It showcases expansion scenarios through easy-to-use interactive visuals. It is adapted to any deployment needs, either for deciding where to create new network opportunities or for growing an existing network, as for example in an environment such as London. Evo-Track supports stakeholders in the electric mobility ecosystem. It provides data services for electric vehicle charging analytics that help operators and providers of electric vehicle-related services to inform their business decisions. Thank you very much for your attention. We hope to connect with anyone interested in our solution.
Hi, welcome again. My name is Michael Hoot. It was really great to hear our first four speakers, Maria, Matthew, Denise, but also actually five here because Daphne and Oytun spoke together. It was quite interesting to see that there was a lot of interest in digital twins. That's obviously relevant in lots of the vertical sectors. We had, at least two talks around the theme of sustainability. And so in that light, I can sort of create a bridge to our next speakers. So I'm really delighted to have Nick Blake here from Hitachi, but also Kostas Pantelidis from Process Systems Enterprise. And I think I'll just want to hand it over to Nick to give a 4-minute presentation before we then have Kostas' talk and then turn to some questions. Thank you, Nick.
Thank you. Okay. Good morning. I'm Nick Blake, and I'm Chief Innovation Strategist and Head of Big Data at Hitachi's European R&D organization. All of our work is focused on delivering environmental, social, and economic value. And specifically, our aim is to make our societies and industries sustainable, resilient, safe and secure, accessible and connected, trusted and transparent, healthy, and of course productive. And this translates into three main areas of research: sustainable energy, green mobility, and what we call a super secure digital Europe. So our mission is to build a sustainable and digital Europe. And the three areas that I mentioned are, of course, overlapping Venns. For example, the transformation we're seeing in energy to support carbon neutrality, including new energy vectors such as hydrogen and energy conversion and storage, impact industry, mobility, campuses, and many more sectors. So it's kind of a horizontal. We've 6 laboratories and locations across the UK, France, and Germany, and we collaborate closely with external organisations, including national innovation funds, such as UKRI and Horizon Europe, as well as world-class universities, including Imperial and Cambridge. And we're actively involved in corporate venturing across a diverse range of areas, including genetics, for precision medicine, digital trust, and energy. Many of our research projects are at the intersection of engineering, or what we call operating technology, and artificial intelligence. So I think today's discussions are quite relevant. Just picking up on a couple of specific examples, and we've got many more, and I'm very happy to discuss our wider work in some of the breakout sessions. Firstly, we're very actively engaged in the development of AI-based autonomous control for cars and mass transport, including trams. And we're currently part of an Innovate UK funded project called Serve City, and we're focusing on the challenges of autonomous driving in congested urban areas. Our development combines traditional engineering and AI to address the challenges of localization, perception, anticipation, and motion control. And the use of AI enables us to make the driven experience smooth and human-like, but the engineering dimensions ensure that those models are safe and bounded in the event that the AI makes perverse or recommendations that are outside those strictly agreed parameters. In the area of digital rail maintenance, we're using a combination of our deep engineering knowledge in that sector and AI using current amplitude vibration and advanced imaging to predict and prevent failure. And we're also working to make the spaces where we travel, work, and socialize resilient, safe, sustainable. And an example of this is another project funded by Innovate UK that combines sensor intelligence and dynamic optimization to reduce congestion in stations, enabling social distancing and driving, hopefully supporting people's safe return to rail travel. But we're facing some challenges. It's all about digital solutions focused on data and AI, but challenges lie ahead, including the adoption and regulation of AI. And we will need to ensure that it's explainable and transparent, ethical, fair and balanced, avoiding drift, safe, often requiring human in the loop, and trusted. And we also need to be aware of increasing levels of regulation, for example, the GDPR and the forthcoming AI Act. So hopefully we can discuss some of these considerations later. Many thanks, Michael.
Yes. So my name is Kostas Pantelidis. I'm one of the founders of Process Systems Enterprise, and now he's CEO and actually CTO, which is why I'm here. I would like to give you our perspective on the role of data science in process modeling. Just one slide on who we are. As Rebecca mentioned in the beginning, we had a spin-out from Imperial going back to 1997. So many years ago, I was in the same position as some of the academics we heard today. Our technology is based on a platform called GPROMS, General Process Modeling System, which we've been developing at a huge pace over the last decades. We started with 2 people, we grew to a couple of hundred. We were acquired by Siemens in October 2019, and since then we've grown by another 100 actually. So now we are about 270 people. It's a very R&D, high technology focused company. We have more than 80 PhDs among those 270. What do we do? First of all, we focus on the process industries, which basically means anything from upstream oil and gas to chemicals, petrochemicals, specialties, pharmaceuticals, food and beverage, consumer goods, the power industry, for example, pretty much anything which is not discrete manufacturing. And our approach is to use models, mathematical models, to optimize all the entire life cycle from early stage R&D to engineering design to operations. So a very wide remit. And if you look at our client list, you will see pretty much most of the major oil and gas companies, both internationals and also national companies. But of course, on the other extreme, pretty much every single major pharmaceutical company is our client. Now, for us, modeling until quite recently meant physics-based modeling, modeling based on the fundamentals of physics, engineering science, and so on. Where does data science come into this? And I have three statements. So you can expect to see three slides in this presentation. And here's a statement that, first of all, purely data-driven models are rarely sufficient for what you want to do. Even when you consider gigabytes of data from operating plants, when you analyze those data, they contain very often very little information. This is not an accident, this is by design. The job of a good plant manager in the chemical industry is to make sure that you get zero information other than a single operating point. So if they're really good at what they're doing, you will almost by definition there will be very little information in that data. When you look at many of the key performance indicators of the process, the things which relate to the product quality, but also the safety of the process, many of those cannot be measured directly. So you are at a disadvantage there if you rely on measured data. And of course, a lot of what we do is design completely new equipment or completely novel equipment in many cases. And of course, there you don't have any data at all. So for all these reasons, a purely data-driven approach isn't working very well for us. What does work for us is a hybrid physics-based and data-driven approach. And the situation there is actually, again, once you think about this, it's quite clear what this is. For most systems of interest to process engineering, there is already some, usually extensive, prior knowledge in terms of what I mentioned before, fundamental physics, engineering science. So you're not starting from nothing. In fact, you're starting from a very good basis. And if you have a shiny piece of equipment like the one I'm showing here, in most cases, you can predict its behavior quite well, just based on fundamental physics. Now, the problem there, of course, is that there are certain secondary phenomena which are much more difficult to capture from first principles. What I'm showing here is what happens to the shiny piece of equipment after a while. Once you start operating it, you start getting, for example, degradation phenomena like catalyst deactivation, things called coking, fouling, and so on. There's wear and tear, and so on. So this model here is not entirely capable of predicting the behavior of this equipment here. However, what we're going to do here is to use data-driven elements to patch the gaps in the fundamental knowledge. We're not throwing the fundamental knowledge away. We combine it with data-driven elements to get models which are predictive, models which can relate the effects of our decisions on the key performance indicators of the process to an accuracy which is sufficient for the business objectives. So this is the second point I want to make. Before I introduce the third point, I need to give you a bit more of the background of what's happening in process modeling in the 2020s. Essentially, we're moving towards something called ultra-large system optimization. Here's a real example. It's slightly disguised, but it's something we've been working on in the last couple of years. What you have here is a network of about a dozen chemical plants. Now, what you would like to do is to optimize this as a single entity. There are very good business reasons why you want to do this. I'm not going to go into this, but the benefits of being able to optimize the whole thing as a single entity are measured in the hundreds of millions of dollars a year. Now, you may well optimize this, but are you going to believe the answer that comes out of the model? And this is, of course, why you need to put sufficient predictive detail into the models. So what appears to be a little blob here, once you expand it, it looks like this. And what appears to be another little blob there, once you expand it, it looks like this. And imagine doing the same thing for every part of this big network. What you end up with is, in practical terms, is a model which is described by millions of equations and variables. Whether those are 100% physics-based or partly physics, partly data-driven elements, it's irrelevant. You have millions of variables and equations. And as mentioned by Matt Piggott, these days we're not going to try and find the optimal operation of this thing by trial and error, because we have hundreds of optimization decision runs, literally hundreds. And so we have to apply rigorous optimization techniques to getting the optimal answer there. And just to make it a bit more interesting, we have to deliver that optimal answer in 10 minutes. This is the real situation. So in situations like this, we have all the predictive accuracy we need, but we cannot code computationally. And what comes to our rescue, increasingly, is techniques based on surrogate modeling. The ability to take certain complex parts of this model and replace them by a much more compact representation derived from machine learning. So hybrid modeling was useful, but surrogate model is a strategic technological element to what we're doing. The key objectives here is to achieve computational efficiency and computational reliability, especially in online real-time applications like what you see here. We no longer run models sitting in front of a laptop and so on. We have models, very complex models of the kind I described before, embedded inside online systems. Of course, what we need to do there is to preserve, make sure that the techniques we use for machine learning preserve the original model's predictive accuracy. Now, as I mentioned, this is strategic for us because for the first time, we can put as much detail as we want to achieve the predictive accuracy, and we decouple this from computational complexity. So this is crucial for what we want to do. So here's my 3 points again. This is all I want you to remember from my talk, and thank you very much for your attention.
Thank you very much, Kostas. Really appreciate that. I think we had a couple of questions already in the chat. I mean, maybe what I should do is sort of have a comment and then turn that into one of those questions, contextualize it. So I mean, it's quite interesting. We had at least 3 talks, and Kostas, this was one of them, where we see deep learning type things being used, but actually they're kind of, within a certain workflow where there's some explicit knowledge, be it physics laws or operational sort of things, constraints and so on. And then the magic, I guess, is in how you compose these elements, right, to bring the benefits to the business. And on a traditional academic research perspective, deep learning is usually seen in isolation, right? So, and there is this. I posted this in the Slack. There's sort of a revenge, an article in the CACM that basically contemplates machine learning researchers should focus much more on the integration, tight integration of knowledge, explicit knowledge in any kind of machine learning frameworks, including deep learning. So maybe, I mean, turning this into a question which was asked in the chat, if companies don't have any experience in ML, how should they actually get started? And I think one of the issues I can see there is they probably have an awful lot of explicit knowledge and operational constraints. How could they take any kind of AI techniques and expertise to put that into their own environment to great benefits? So anyone who would like to have some thoughts on that?
I can try to start.
Great.
I mean, I'm obviously coming from a background who could learn and apply these techniques on my own, but I'm also aware that the new capabilities of a lot of different coding languages and software packages, they come with very standardized, easy to start machine learning applications. So it still requires some technical backgrounds, but it's not as hard as it was maybe 10 years ago to access these capabilities. And they're being tested, and there are various communities to kind of foster this kind of applications. I think, I mean, it's not surprising, but the machine learning community, or whatever you might want to call them, because people have different names for similar techniques, they're quite helpful and responsive to these. I started learning this on my own, and I think companies would be able to access these resources quite easily as well.
I may make a comment on this, just to build on that point. Most organizations, when they do have deep domain experience in their businesses, whether that's in engineering or whether it's in finance. But at some point, if they want to get into this, they're going to have to hire some data science experts. We've all had to build these organizations kind of from the ground up, because this is a fairly new industry. But what I found is that when you fuse or combine the experience that you can bring in by hiring in data scientists with the deep domain expertise that's in the organization, and put those together and connect them, that can be quite successful and is a good place to start.
If I
That's a
can
great
add to
point.
that,
Yeah, Chris?
what is very important, obviously, I fully agree with Oytun, the tools that they're a lot easier to use than they used to be. And getting people in is very difficult these days because there's a lot of demand for data scientists. But from the company's point of view, what is very important is clarity of the objective. Why are we doing this? We're not doing this to bring in AI and machine learning. We're doing it to solve a specific problem that we cannot solve now. That's, for us, for example, we did decide that we will push physics as much as it will go, and we will only use machine learning to patch the gaps, as it were. Okay. Other people may decide that it's a different thing, and we want to do it as easily as possible, and just putting a lot of data from machine learning may be easier than putting in a lot of physics and maths. So you have to have a clarity of objective. Otherwise, the whole thing becomes, there's a risk of the whole thing becoming sort of self-serving exercise.
Yeah, thanks. And I guess that's also a point about larger companies, which often do these things in innovation departments, right? But that's quite remote from production and product ownership and so on. And so it's maybe also a question for startups. How can you maybe engage with large companies, not going through the innovation branch, but going straight to product owners? Yeah, I mean, maybe sort of related to that, I think there was a question to Maria, Matt, and Costas, that applications of ML are more critical than what some might be used to, like recommendation systems and so on the web. So how do you validate these models and how they actually then run in your products? Anyone would like to? I think also Nick commented on ethics and explainable AI and all these things. So maybe we can explore this a little bit.
I could start, because
Yeah,
actually it's a comment I want to make also to the previous question that relates here. So I think that the user companies at the end of the day have the most important part of the experience, which is the process itself. Nobody knows it better. There is no one knowing better what they want to do than themselves, right? So all the feedback, the most critical part of the feedback in terms of usability of these tools comes from them. And then through the collaboration with people working at the forefront of creating essentially those tools, I think we can achieve a huge knowledge transfer element from the academic groups or startups to the big organizations. In terms of how we technically validate those models, I can talk about my experience. We collaborate very closely with industries who are looking into using such software solutions. And so we get data directly from them, wherever this is possible, because one of the points that Kostas made during his presentation, we see it very often as well, that there are cases that there is no data, especially when we work in process development, which is a very big part of what we do in my lab. So there's a huge element of discovery that feeds back to why should we actually use mechanistic models in tandem with machine learning. So I feel there's like a lot of gain in the combination of those tools. But generally, yeah, the validation comes from real world data and expert feedback.
Yeah, thank you very much, Maria. I think this also touches nicely onto a question that was asked for Dennis. I think how do you take great innovation in machine learning that seems fairly disruptive in some sense, but reconcile this with existing realities like the technology stack around wireless? So maybe you can try and answer that.
So that's definitely a challenge. I mean, in like many other technologies, back compatibility is a challenge. So specific to our kind of solution, I think the answer is it's as compatible as you like, in the sense, if you want to put those constraints, then the gains are less, but they are still there, just like in many other things. So that has a cost. And if you have an application, like let's say if you can have a standalone application, you want to build a drone and you are not bound by standards, then obviously it's going to be much better. The gains are much more significant. If you want to use this for something like the, let's say, 6G standard, next cellular radio standard, obviously it has to be back compatible. Then you will have certain constraints. There will be some losses, but it still can be used. But I think I want to connect to the previous discussion. It's very important, I guess, to get even for in my industry, kind of wireless, right? So these are huge companies. I think many of them now get into AI, so they have, as you said, like R&D departments, so they want to explore. But most of the people, that actually develop these technologies are not aware of all the details, right? So it's something that they are exploring. They don't want to fall behind, but they are not completely, they may not even believe that this will have an impact. And I think something distinguishes wireless from some of the other areas is that, so this has been a very successful industry. So it's not like, some of the problems that we couldn't solve any other way, so we want to bring AI. Whereas, we have 5G, it's in a way, it's a very miraculous technology, what we can do with it. So then people are very suspicious that, okay, what can AI bring to that? But obviously there are, like in everything else, there are many things that it can bring. But this is, I think, what Kostas was saying also in the presentation, that this domain knowledge together with AI. I don't think, like if you can just bring a data scientist put there and then they will, I don't expect that will bring much, but someone with the domain knowledge and with the AI expertise is much more valuable for both startups and I think the larger companies.
Yeah, thank you, Denis. Let's see. I mean, maybe another thing to touch on is, because we saw at least two talks, Nick and Daphne on sort of mobility, right? Green mobility, but also multimodal transportation systems, and these are quite complex things where there's different degrees of autonomy and so on. I was just wondering, how AI innovation might be situated in there, given the regulatory or policy uncertainty in this kind of space. Maybe Nick can also comment on this, because, for example, with charging stations, it's not clear, will this be mostly done in private homes at the end of the day, or will this be more a public infrastructure and so on? And what does that mean for businesses as they want to invest in AI and machine learning to accommodate these kind of future technologies? So I think it will be interesting to hear some views on this.
So the regulatory side of it is kind of a moving platform, really, and particularly with regard to areas like autonomous driving, it's quite complicated. Not only the regulatory side, but also the accountability side, and those standards and regulations are still emerging. With regard to EV charging, that also puts some massive complications on the energy networks, and we're going to require a combination of domestic depot and public charging capabilities, and the opportunity to use AI to optimize that whole network. That is a significant area of research for us.
Yeah, that's interesting. I mean, that also seems to suggest there's more need for what people call co-opetition, right? Because you can't just sort of compete head on head in such ecosystems. You need to also kind of collaborate within the competition. Is that a sort of a fair comment to make? Or
this area certainly requires an ecosystem approach. Yes, and so it also may require organizations that were previously in competition to collaborate.
Yeah.
No one's going to do this on their own, because the dimensions of this are so large, regarding from the optimization of the charging, to the battery use, the circularity of the battery, to the decisions about when you charge, when you dispatch, etc., etc. Yeah. And we're just starting to uncover some of these complications.
Right.
But yes, you are correct.
Just to
add there, I suppose the cooperation would be well, highly favored in this aspect, because without the companies working together, there will be a lot of redundancy in the infrastructure, and there will be a lot of well, unoptimal expansion in a way, because all these companies will put them in places where they could potentially profit, but that doesn't necessarily mean that the network will be efficient or profitable in the future, because these infrastructure is stationary, so it's not that you can just move it the next day if it requires a different setup.
Yeah, I guess also interesting, this is a very social ecosystem, with lots of players and participants, and then it needs to be super secure for the digital Europe, right? Like Nick was saying. So that's an additional challenge, I guess, there. Maybe I can sort of turn to another aspect, which was maybe only touched upon in the talks. I mean, so AI and engineering, I'm also thinking of like material sciences and so on, so I mean, Matt was talking about the design space and how AI helps to reduce the complexity in this large space by still exploring large portions of it, right? And so I'm kind of wondering, if there is a real potential here in machine learning in particular, with combination of physics laws and chemistry, to make some really big advances in smart materials in the future. So maybe any thoughts or comments of experts in that domain? That's not my expertise. So.
I mean, nor mine, but I could maybe just comment, sort of amplifying what Kostas was saying, that as well as domain specialism, if you know what the equations are that are governing all or a significant portion of your system, you're a bit foolish to just throw them away and take a purely data-driven approach. And that comes back to the verification question. So in my talk, I was trying to argue that it is kind of like a bit of a sort of a dial you can turn up. So how much filling in the gaps, as Kostas called it, how much filling in the gaps do you do versus trying to do things in a process, physics, or mechanistic based? So I think that if maybe in many areas of science and engineering, we're lucky if we have some underlying equations, we should look to use them. By doing some expensive simulations using those equations, we can generate verification data. So depending on exactly how many of the gaps we fill in using data-driven approaches, we can generate faith in those from a purely synthetic computational avenue. So I think that when domain specialism, we're lucky when we have the equations. We shouldn't throw them away. And this is, I think, why the combination of data-driven with physics, process, or mechanistic-based models is quite a hot topic now. People are realizing that it's not one or the other. The combination is really where the power and taking the best of both worlds, trying to mitigate the weaknesses. And the weaknesses in doing everything purely computationally is it's very expensive. So myself and Kostas both said you can't then use that within a loop that you want industry to run in 10 minutes and come up with an optimal design.
And I think one area that we as an industry need to develop in is our architecture skills that seem to have been subverted in this chase towards data science and ML. What we found really important is how to break down a problem into its constituent parts. If you try to apply an amorphous machine learning model to solve the challenge of autonomous driving, you can do that, but you can't unpick it and you can't bound it with the engineering. So you need to break that problem down. So you might use artificial intelligence to perceive the outside world. You might then use it to anticipate the decision and to translate that into a motion control. There might be 3 or 4, if you include localization, separate ML models. But if you conflate them into one model, and I think this is something that Kostas was talking about, actually your ability then to unpick or bound it becomes severely limited. But what we're finding now is that although we break these things down and we bound each module by engineering, they're actually interconnected. And those interconnections between those ML models are actually very important as well. So, for example, I think a child may be walking into the street, or there may be a risk That's my perception. I then decide I might need to anticipate that, but then I need to sharpen my focus, my perception, right, iteratively on that child. Is he going to walk into the street or not as time passes? So we've actually got interactions between these ML models now that we need to think about. So we need to keep them separate, but we also need to understand the interconnections between them.
That's very interesting. I mean, we have to sort of wrap up in a minute or so, but I just wanted to say this reminds me very much of the work by US NIST, for example, and there's also UK agencies in the space on frameworks for multidisciplinary engineering and psychophysical systems, where you have timing, you have security, you have all sorts of separate concerns that all need to be reflected as you map out requirements and start to combine things in a system of systems. I wanted to maybe sort of summarize in a way some of this discussion by saying, I think there's a real need here also in this new college initiative of IEX around AI and machine learning and data science to have postgraduate taught courses maybe that really focus on this idea of it's not just machine learning or some isolated thing, it's understanding how some of this would be situated in a discipline in a real sort of product environment, and I think we could actually design some courses around that theme where it wouldn't necessarily just be for chemical engineers or some specific discipline, but actually to create a transferability across these disciplines. And I could imagine, and that's partly a question to you, although we're almost out of time, there might be some appetite in industry for employees to actually attend such courses. Maybe a quick spontaneous reaction to that. I see heads nodding, so maybe I'll take that as a response. Okay, so in that sense, I wanted to thank all of you, for your presentations. It was very fascinating and the stimulating and really insightful discussion. And I'm afraid I have to hand it over now to Chris to wrap things up. Thank you, Chris.
Thanks very much, Michael. My name is Chris Parker from the Imperial Business Partners Programme, and I work with the Enterprise Division at the college, creating opportunities just like this one for industry and academic expertise to connect and collaborate. I'd like to take the opportunity to thank the speakers and the chair for such an interesting discussion. Thanks also to our online attendees for staying with us for the duration and to everyone involved in the delivery of today's event.